Jai Hind learners, I am Dr. Supratim, Associate Professor Swami Vivekanand Subharthi University, Meerut, and in today's e-lecture, we are going to discuss about microwave semiconductor devices. Moving forward, the topics that we are going to discuss today are microwave semiconductor devices classification, avalanche transit time devices, IM pad devices, IM pad structure and its operation, followed by trapet operation, followed by the conclusion. So let us move forward and go deep into the topic. Microwave semiconductor devices. A microwave semiconductor device, they are nothing but electronic components which are designed to operate at microwave frequencies, that is typically in the range of 1 gigahertz to 300 gigahertz. On the other hand, they are crucial for various applications in telecommunications, radar systems, and as we discussed in the previous lecture as well, in satellite communications and many more applications associated with it. Moving forward, we concentrate on the classification of microwave semiconductor devices. So we are going to discuss classification of microwave semiconductor devices. As you can see in the classification of microwave semiconductor devices, they are having variety of divisions. One of the most important divisions that we can see here, as you can see, is the microwave transistor time devices, that is BJT, HBT, avalanche transit system, which again has red, IM pad and trapet as the main versions that are associated with the division. Apart from this, we can also see that there are various divisions, for example LSA diode, gun diode, Barrett, CX and KU bands associated with the TEDS devices. So moving on, what we can see is that you can see LSA limited space charge accumulation is there. IM pad, it means impact ionization avalanche transit time device, followed by trapet, that is trapped plasma avalanche triggered transit device, followed by Barrett, that is barrier injected triggered transit device, avalanche transit device, etc. These are some of the portions that we can concentrate on. Now, avalanche transit time devices. It was proposed by W.T. Reid in 1958 that the delay between the voltage and current in a material will be avalanched together with transit time through the material, by which it is possible to make a microwave diode which exhibits negative resistance. These type of devices are known as avalanche transit time devices. Types of avalanche transit time devices. Mainly, we can see there are three types of microwave transit time devices, and these three types are known as IM pad, that is impact ionization avalanche transit time device. Then we can say trapet, that is trapped plasma avalanche triggered transit time device, followed by Barrett, that is barrier injected transit time device. Moving on, in the further category, we can say that the purpose of avalanche and transit time devices and how we can modify them, that can be there. So avalanche transit time devices or semiconductor microwave devices, what happens is that like conventional ordinary vacuum tubes cannot be used at high frequency because some parameters generate complicated situations. Now these complicated situations can be of various types, and these parameters mainly are what we can show here: the inter-electrocapacitance effect, number 2 lead inductance effect, number 3 transit time to overcome the above problems. Okay, so in order to solve these problems, one should use either a high frequency transistor or some other special type of semiconductor devices like negative resistance and non-linearity devices in the operation, that makes special devices, that is the likes of, you can say varactor diode and other similar devices. For an example, say pin diode, trapet and so on. We can also use tunnel diode and gun diode along with high frequency transistor. They are suitable for their operations in which region? Obviously they are suitable for operations in the microwave region. Okay, so these are some of the benefits that we are going to have in case of this. Now bulk semiconductor devices, for example gun diode, ordinary PN junction diodes, varactor and tunnel diodes, okay, modified PN junction diode, IM pad, trap pad, pin diodes such as PN or PIN die. These are also some of the examples. Now microwave semiconductor devices have been developed for various applications like detection, mixing, frequency multiplications, attenuation, switching, limiting application or oscillations, etc. Now if we move forward, we can say that there are some of the advantages also that are associated with these kind of devices. So these kind of devices have low cost, that is one of the primary advantages, small size, less weight, low noise, greater bandwidth, lesser switching time, and they can also be employed in microwave integrated circuit and other improvements in performance characteristics for achieving the above functions. Right? Now we are going to discuss about IM pad diode in detail. It will be having the structure, basic structure and its explanation along with it. So this is IM pad devices. So what is it? Impact ionization avalanche transit time device. An IM pad diode, that is impact ionization avalanche transit time device, is a form of high power diode used in high frequency electronics and microwave devices. And what is the range they operate at? They operate between 3 to gigahertz. Okay, so this entire thing is having the range of 3 to 100 gigahertz. Okay, it has many forms like abrupt junction and pin diode. Here what happens is that the positive, that is zero sign, indicates a high level of doping and it stands for intrinsic or pure silicon. The two common type of IM pad structures are SDR and the other one is DDR, that is single drift region and double drift region. Now we are going to discuss the manufacturing and other portions of the IM pad and its structure. Now IM pad diodes can be manufactured from GA, SI, GAS or INP. However, GAS, that is gallium arsenide, provides the higher priority. Because of its high efficiency, the highest operating frequency and least noise figure, it is preferred. But the fabrication process is more difficult and costlier than silicon. As you can see, this is PNIN portion. Okay, it has high power capability. These diodes are used in variety of applications from low power radar systems to various other processes. Okay, so this is the portion of the IM. The concept of operation. Okay, one of the concept of operation of this deals with the major drawback, that is IM paired diode is the generation of phase noise and it results from the statistical nature of the avalanche process. Nevertheless, these diodes make excellent microwave generators for many applications. Okay, so moving on, the concept of operation that we are going to discuss. Here you can see that this is the avalanche region, this is the drift region and this is the doping portion. Now what happens is that a very high voltage, that is 400 kV per centimeter, 400 kV per centimeter. Now this is very high and a normal diode would easily break down under this condition. But ion pair diode is constructed in such a way that it will withstand these conditions repeatedly. Such a high potential gradient back biasing the diode causes a flow of minority carriers across the junction. Now what happens in case of this entire structure that we are seeing, where electrical field and positions are also considered, that it is now assumed that oscillations exist, and we may consider the effect of a positive swing of the RF voltage superimposed on top of the high DC voltage. Electron and hole velocity has now become so high that these carriers form additional electrons and holes by knocking the portions out of the crystal structure. By this so-called impact ionization, we have two steps to understand the process and its operation. Step 1. These additional carriers continue the process at the junction, and the voltage will be exceeded during the whole of the positive RF circle. Okay, and similarly the whole of the positive RF cycle will continue expecting and continue experiencing this. The avalanche current multiplication will be taking place this entire amount of time. Since avalanche is a multiplication process, it is not instantaneous, or we can say it is a cumulative process. That means it adds up with the system. This process takes time such that the current pulse maximum at the junction occurs at the instant when the RF voltage across the diode is 0 and going negative. A 900 phase difference between voltage and current has been obtained. Step 2. This is the second step that we are discussing about. The current pulse in the ion pair diode is situated at the junction. However, it does not stay in this way because of the reverse bias portion. Because of this reverse bias portion, what happens? The current pulse flows to the cathode. That means this portion. And because of that, a drift velocity, depending on the presence of the high DC field, the system works. Okay, the time taken by the pulse to reach the cathode, it depends on the thickness of the highly doped N+ layer. So the thickness of this is an important factor for this. Okay, now drift space is adjusted such that the time taken for current pulse to arrive at the cathode corresponds to further 900 phase difference, 90 degree phase difference, sorry. Thus voltage and current are 180 degree out of phase, and a dynamic RF negative resistance has been proved to exist. In summary, negative resistance phenomenon is taken into account by using the impact multiplication avalanche effect. It causes the minority current to lag the microwave output by how much? By 90 degrees. And because of this, the effect of transit time through the drift region, it happens. This results in the external current lagging the microwave voltage by a further 90 degree phase shift. So all in all, what we have is that we have a system where the entire process comes together with the help of the electric field, various positions, the avalanche diode region, the drift region, and from anode to cathode transfers with the help of the thickness and other properties associated with P and N junctions. These all things combined together come and they are utilized in the basic working. That is, a very high voltage 400 kV per centimeter is applied to the ion pair diode, resulting in a very high current. A normal diode would easily break down under this condition, but ion pair diode is constructed such that it will withstand these conditions repeatedly, no matter how many times you use them. Such a high potential gradient that biasing the diode causes a flow of minority carriers across the junction. These are some of the highlighted points forward to the trapped devices. Okay, a trapped device, that is a trapped diode, is a trapped plasma avalanche triggered transit time diode. It is a very efficient microwave generator. It is derived from the word ion pair diode and is closely related to it. The basic operations of it is in an oscillator and a semiconductor p-n junction diode, reverse bias to current densities well in excess of these encountered in normal avalanche operation. It is generally also very useful in microwave operations. Okay. High peak power diodes are typically silicon or PNN structures with the N type, that is depletion region, varying from 2.5 to 12.5. As you can see here, this is a basic structure of a trapped diode. The doping of depletion region is generally such that the diodes are punched through at the breakdown. The device P plus region is already there and kept as thin as possible at 2.5 to 7.5 pm. The trapped diode diameter ranges from as small as 50 for PW operation to 75 for other operations at lower frequency for high peak power devices. Good result from trapped diodes are below 10 gigahertz. So now we concentrate on the principle of operation. A high field avalanche zone propagates through the diode and fills the depletion region with a dense plasma of electrons and holes that become trapped in the low field region behind this particular zone of ours. In this entire process, the P plus and N plus and N junction, that is P and N portion, we have highlighted, and that plays a major part in the construction of the trapped diode. Now we are going to look at the basic working. As you can see, there are various portions mentioned over here. This is part A, part C, part B, part G, and so on. So using these and the graphs, we can calculate and know the operations. Some given steps are being followed. So let us do that. So first we will discuss from our part A to part B, this portion. So what happens is, at the instant of time at point A, the diode current is turned on. Now this current only charges the carriers present, and they are those which are caused by the thermal generation. The diode initially charges up like a linear capacitor. Curve AB shows the magnitude of the electric field above the breakdown voltage. Now look at curve B to curve C. Here, if you look at this particular graph, you will see when a sufficient number of carrier is generated, the particle current exceeds the external current and the electric field is depressed throughout the depletion region, using the voltage to decrease from point B to point C. What happens? A dense plasma formation is there. A dense plasma formation is there. So this takes care of our part B to part C. Next comes curve C to D, this curve. What happens here? During the time instant, the electric field is sufficiently large for the avalanche to continue, and the dense plasma of electrons and holes is increased. In this plasma of electrons and holes, some of the electrons and holes drift out of the ends of the depletion layer. Thus this particular field is further depressed and traps the remaining amount of plasma. It traps the remaining amount of plasma. So we have covered 3 portions of the curve till now. So next operation deals with the portion D to E. Here what happens, a long time is required to remove the plasma. Here what happens is that the plasma charge is very large compared to the charge per unit time in the external current, this current. Now at point E, here the plasma is removed and voltage increases from D to E. So this takes care of the process from D to E. Next portion of the curve ranges from E to F. What happens here? Here the electrons remain in one of the end of the depletion region and a residual charge of volts in the other end. As the residual charge is removed, the voltage increases from point E to point F. At point F, all the charge that was generated initially has been removed. So all the charge that was earlier there is removed here, is removed in this portion. The final stage of this operation is from F to G, that is from here to here. The diode charges up again like a fixed capacitor, right? At point G, the diode current goes to 0 for half a period and the voltage remains constant at voltage VA until the current comes back at the entire cycle will then repeat. So this is how from A to B, B to C, B to E, E to F and F to G the curve goes on, involving various parameters from charging to current to voltage to residual extraction, plasma extraction and plasma formation, in order to continue our journey of the basic working of trapped diode in the light of the working of IMPATT, IMPAT diode. So in this entire chapter we have discussed the overall concepts of microwave semiconductor devices, followed by microwave semiconductor devices classification, avalanche transit time devices, IMPATT, IMPAT devices, IMPAT structure and its operation, trapped, its structure and its operation with the help of a graphical method, and finally we conclude this topic where we have understood the basics of microwave semiconductor devices. I hope this lecture has been informative to you and thank you for watching. We will again meet in a future series of lectures. Till then, thank you and Jai Hind.